Imagine looking up at the night sky and seeing stars, planets, and moons moving with seemingly perfect precision. For centuries, we believed the universe was a grand clockwork, predictable and orderly. But what if I told you that just adding one more body to this cosmic dance can turn everything we thought we knew upside down? What if the very laws that govern motion, the same laws that guided Newton's genius, suddenly lead to chaos, unpredictability, and astonishing complexity? Today, we are about to dive into one of the most fascinating mysteries in physics, the three-body problem. It is not just a mathematical puzzle, it is a window into the hidden intricacies of the cosmos, a challenge that has pushed the boundaries of human knowledge, computation, and imagination. From the delicate dance of planets to the rise of chaos theory, the three-body problem has reshaped our understanding of physics, revealing that even in a universe ruled by laws, surprises await at every turn. When we think about classical physics, we often imagine a clockwork universe where everything moves in precise, predictable ways. Newton's laws gave us that comfort, especially in the case of two interacting bodies. Planets orbit stars, moons orbit planets, and we can calculate their positions centuries in advance with astonishing accuracy. But the moment a third body enters the scene, that elegant predictability begins to crumble. The three-body problem, deceptively simple to state, just find the motion of three masses interacting through gravity, hides within it a secret of nature's complexity. Unlike the two-body case, there is no general formula or neat solution that works for every configuration. Tiny changes in initial positions or velocities can grow exponentially over time, creating behavior that seems almost random, even though it is governed by deterministic laws. This phenomenon, which later formed the foundation of chaos theory, illustrates that predictability is not always a guarantee of determinism. In practical terms, this means that while we can understand the rules, we cannot always foresee the outcomes with absolute certainty. Orbits that seem stable can twist into erratic paths, and motions that appear regular can suddenly shift into chaotic spirals. This realization forced physicists to rethink the very idea of certainty in nature. It also sparked a new approach to science, one that focuses not only on exact solutions, but also on probabilities, patterns, and simulations. By studying the chaos inherent in three-body interactions, scientists gained a deeper appreciation for the subtle complexity of the cosmos, understanding that even the simplest systems can hide infinite possibilities. It challenged the classical notion that the universe is entirely predictable, opening minds to the idea that some aspects of physical reality are inherently sensitive to tiny variations, a lesson that resonates across disciplines from astrophysics to climate science. The three-body problem is more than just a puzzle about celestial motion, it is a gateway into the fascinating world of nonlinear dynamics. In simple systems like a swinging pendulum, forces and responses are proportional, double the push, double the swing. But when three bodies interact through gravity, the rules change completely. The system becomes nonlinear, meaning small differences in starting positions or velocities can produce dramatically different outcomes. This sensitivity to initial conditions is what makes the three-body problem so intriguing and so elusive. One moment, two planets might dance around each other in elegant harmony, and the next, a slight shift sends one hurtling unpredictably through space. Nonlinear dynamics introduced physicists to a universe where linear intuition fails, where cause and effect do not scale in straightforward ways. It showed that simple laws can give rise to extraordinarily complex behavior, a concept that extends far beyond astronomy into fluid dynamics, weather systems, and even economics. By studying the nonlinear interactions of three gravitationally bound bodies, scientists learned to embrace uncertainty and to seek patterns not in exact positions, but in the structure of motion itself. Orbits were no longer just paths, they became landscapes of possibilities, revealing hidden symmetries and chaotic zones. This insight also demonstrated that nature's complexity often emerges from interactions that are fundamentally simple in their rules, but nonlinear in their effects. The three-body problem thus became a laboratory for understanding the mathematics of complexity, inspiring generations of physicists and mathematicians to explore systems where intuition breaks down and computation, approximation, and visualization become essential tools for discovery. The three-body problem did not just challenge our understanding of physics, it transformed the way we approach scientific calculation itself. For centuries, physicists relied on elegant equations and analytical solutions to describe the motions of planets and stars. With two bodies, Newton's laws provided precise formulas, allowing exact predictions. But as soon as a third body was introduced, these formulas broke down. No general solution exists that works for every possible arrangement of three masses interacting gravitationally. This barrier forced scientists to rethink how they could explore such complex systems. The need to understand, predict, and visualize the motion of three-body systems sparked the development of computational methods. Instead of seeking exact solutions, physicists began approximating motion step by step, using iterative calculations to simulate trajectories over time. This shift was revolutionary. It moved physics from purely theoretical calculation toward a computational and experimental mindset, long before modern computers existed. Scientists used mechanical calculators, tables of numbers, and later electronic computers to explore behaviors that would have been impossible to capture by hand. Computational experiments allowed them to map chaotic zones, identify stable orbits, and uncover unexpected patterns, revealing a richness of motion previously hidden. The three-body problem thus became a proving ground for numerical simulation techniques, from Runge-Kutta methods to modern high-performance algorithms. It laid the foundation for computational physics as a discipline, demonstrating that some of the universe's deepest secrets can only be understood through careful approximation, simulation, and iterative exploration. By embracing computation, physicists gained the ability to explore not only three-body systems, but countless other complex phenomena, from the motion of galaxies to climate dynamics, opening an entirely new dimension of scientific inquiry, where insight comes not just from pen and paper, but from the power of calculation itself. The three-body problem fundamentally reshaped our understanding of celestial mechanics, revealing that the motion of planets, moons, and stars is far richer and more intricate than previously imagined. In the simple two-body scenario, orbits are predictable and well-behaved, ellipses, circles, or parabolas that follow Newton's laws with precision. However, adding just one more gravitational player introduces a delicate interplay of forces that produces surprises at every turn. Orbits that initially appear stable can drift, resonate, or even collide over long periods, demonstrating that multi-body interactions are far from simple. By studying these interactions, physicists discovered phenomena such as orbital resonances, where gravitational influences lock bodies into synchronized patterns, and chaotic zones where slight differences in initial conditions can lead to radically different paths. These insights helped explain irregularities observed in the solar system, such as the unexpected eccentricities of asteroid belts, the migration of planets, and the subtle perturbations in lunar and planetary motion. Understanding these multi-body dynamics also became essential for space exploration, where plotting trajectories for spacecraft requires anticipating complex gravitational interactions among planets, moons, and even artificial satellites. The three-body problem showed that celestial mechanics is not just about static laws, but about dynamic systems that evolve in ways that challenge intuition. It revealed hidden structures within chaos, demonstrating that even within unpredictability, there are islands of order and patterns that emerge over time. This perspective inspired generations of astronomers and physicists to develop new tools, from analytical approximations to computational simulations, to study planetary systems, star clusters, and galaxies. In essence, the three-body problem transformed our view of the heavens from a simple mechanical clockwork into a living, dynamic network of interacting forces, where motion is a dialogue between stability and chaos, precision and unpredictability, and revealed the true complexity behind the beauty of the cosmos. The three-body problem marked a turning point in the transition from classical physics to a deeper, more nuanced understanding of the universe. Classical physics, built on Newtonian determinism, promised that given the initial conditions of any system, its future could be predicted with certainty. For two-body systems, this worked beautifully, but the addition of a third gravitational body shattered that certainty. The three-body problem revealed that even with perfect knowledge of positions and velocities, outcomes could be wildly different due to extreme sensitivity to initial conditions. This unpredictability challenged the classical worldview and hinted at the limits of deterministic thinking, laying the conceptual groundwork for modern physics. It demonstrated that while laws of motion are precise, the evolution of complex systems is inherently probabilistic in practice. This shift of perspective resonates with ideas in quantum mechanics and statistical physics, where uncertainty and probabilities become central, and exact predictability gives way to patterns and distributions. The problem also inspired new mathematical frameworks to describe complex behavior, bridging the gap between simple equations and the chaotic realities they govern. Physicists began to appreciate that reality is layered. Classical mechanics works in broad strokes, but deeper understanding requires embracing complexity, computation, and probability. The three-body problem thus serves as a microcosm of the philosophical evolution in physics, teaching that the universe is both lawful and unpredictable. By studying it, scientists were forced to reconcile classical intuition with the messy, intricate behavior of real systems, preparing the way for explorations into quantum systems, nonlinear dynamics, and the rich field of chaos theory. It showed that modern physics is not a rejection of classical laws, but an expansion, a recognition that the universe contains layers of complexity that demand new tools, new thinking, and a willingness to embrace uncertainty while seeking underlying order. The three-body problem is not just a technical challenge in physics, it carries profound philosophical implications about how we understand the universe. At first glance, it is a purely mathematical puzzle, but at its heart lies a deeper lesson about the limits of human knowledge and the nature of reality. Classical physics once promised a clockwork universe where perfect measurement and calculation could reveal the future with certainty. The three-body problem shattered this notion by showing that even with complete knowledge of initial conditions, outcomes can diverge in unpredictable ways. This sensitivity to initial conditions, a hallmark of chaos, forces us to confront the idea that unpredictability is not always due to ignorance or error. It is embedded in the structure of nature itself. It teaches humility, reminding scientists and observers that the universe is more intricate than any simplified model. Beyond mathematics, this problem inspires reflection on the broader patterns of life and existence. Systems that appear orderly can harbour hidden complexities, and apparent randomness may conceal deeper structures. It challenges the human desire for certainty, encouraging us to embrace ambiguity, to look for probabilistic truths, and to explore patterns rather than expecting absolute predictability. Philosophically, it bridges science and existential reflection, suggesting that the universe is both deterministic in law and unpredictable in outcome. By studying three-body dynamics, we learn to appreciate the elegance of complexity, the subtlety of interactions, and the beauty of a cosmos that is simultaneously lawful, mysterious, and endlessly surprising. The lessons extend far beyond physics, influencing our understanding of chaos, stability, and uncertainty in systems ranging from planetary motion to ecosystems, economies, and even human behavior, offering a window into the profound interconnectedness and unpredictability inherent in the natural world. In exploring the three-body problem, we have journeyed from the precise orbits of classical physics to the chaotic dance of multi-body interactions, uncovering a universe far richer and more intricate than we ever imagined. This problem challenged centuries of assumptions, pushed the boundaries of computation, and reshaped our understanding of celestial mechanics, nonlinear dynamics, and even the philosophical nature of reality. It teaches us that unpredictability is not a flaw in the universe, but a fundamental feature, a reminder that complexity and beauty often arise where certainty ends. The three-body problem inspires humility, curiosity, and the courage to explore systems that defy intuition, showing that even in apparent chaos, there are patterns waiting to be discovered, and laws guiding the cosmos in ways we are only beginning to grasp. As you continue your journey in understanding the universe, may this exploration remind you to embrace challenges, to value curiosity over simplicity, and to never fear the unknown. Every complex problem, like the three-body problem, carries within it the potential for discovery, innovation, and insight beyond imagination. Good luck in your studies, your explorations, and your pursuit of knowledge. Thank you for joining this journey, for opening your mind to the wonders of the cosmos, and for daring to see the universe not just as it appears, but as it truly is: intricate, dynamic, and endlessly fascinating.